Good. So I finished the topic that I started yesterday, which is the reacceleration and how we can put the information that we got from second order reacceleration, second order Fermi acceleration into the transport equation. This transport equation that I wrote yesterday and that I will remind in a while contains space-dependent derivatives and derivatives in the momentum or in energy space. And we were going to derive this energy-dependent part of the equation by the Fokker-Planck equation, which is a very generic equation which takes into account the diffusion, in this specific case in momentum, using the principle of detailed balance. So the principle of detailed balance got to this term, which I told you we don't derive here, but you can do in a pretty easy way by Taylor expanding it. And we put this into the Fokker-Planck equation. The energy-dependent part of the Fokker-Planck equation is the derivative over P, and then we have the average of the variation of the momentum times the distribution function, and then we have 1/2 d over dp, and we have there is a discontinuity in the blackboard, so plus 1/2, and it was the derivative over p, delta p variations over the time times the distribution function. So this is just the part, and then we have the partial derivative over time. So if you put 1 into 2, you get the following expression for the energy-dependent equation that regulates the momentum change, which is delta p times df over dp. So this is the portion of equation that we have to insert in our transport equation, because the particles, as we have seen together yesterday, do not only diffuse in space, but also diffuse in energy or in momentum. Usually people define a diffusion coefficient, sometimes called kappa or d, depending on the authors that you are reading. It is the same, which is 1/2 delta p divided by the time in which this shift happens. Often we write, as I did yesterday, this part of the equation directly as a function of energy, and take into account the fact that beta is the Lorentz factor. You can also write, it's straightforward to decide that this equation is the derivative over the energy beta square k, which is always a function of the energy, dn over d, where I, using the notation of our transport equation. So this is the derivation. And before changing a little bit the topics, let me derive in an approximate way the correlation that there is between this coefficient, which is a coefficient in momentum space, and the diffusion coefficient in space, in the real space. The point is that there are the magnetic fields in the galaxy, and I show the first and the second lectures. They are responsible for both the diffusion in space and the diffusion in energy. So there must be a connection between these two quantities. It is the same magnetic fields that shift the energies and make the pitch angle change and the particle diffuse randomly in these magnetic fields. An intuitive way of seeing this can be the following. So let me use this notation. This is the diffusion coefficient in space. I just wrote XX to say that it is really the space, the physical space. And from kinetic theory, one can derive an approximate expression. If you take the lecture that I gave the first day, you can understand this approximate result, which is more or less 1/3 the traveled space squared divided by the time in which this diffusion takes place. This space is run by the particle. And also dimensionally, this is kiloparsecs squared divided mega year or similarly. And then we have the speed is written in this way, and we can rewrite this expression as v squared tau. And now we want to write a similar expression for the coefficient in momentum space, for the diffusion coefficient in momentum space. And from similar arguments, you can see that it is, let's say, this number 1/3 for not the travel distance, but the shift in momentum, and divided by tau. We have also seen, or anyway we can understand, but from the lectures of today, that the shift in momentum is of the order, or VA, over V. And if you put these two terms connected via tau, which is in one place and another, so this is 1/3 p squared VA squared divided v squared tau. And then you can written tau in terms of the diffusion coefficient in space, and that brings you to the connection between the diffusion in space and the diffusion in energy coefficients. And this is approximately V, a coefficient p squared alpha and velocity squared. So this is an approximate derivation. You can, if you're interested, see a very short paper by Thornbury and Luke Drury, written a few years ago, in which they make this kind of reasoning. This coefficient, then you can compute it exactly depending on the exact theory you are dealing with. But what I want to emphasize here is that the two coefficients are inversely proportional. And that makes some sense, because make the hypothesis that the turbulence is very high. If the turbulence, the magnetic turbulence, is very high, then the shift in momentum is very high, because the scattering between this particle is very efficient. So particles change energy in a very efficient way. But in this situation, dxx, so the diffusion in space, is suppressed, because these same turbulences prevent the particles to travel freely. So it is just the opposite of free motion. And the same reasoning is for the opposite situation, in which the turbulence is low. If the turbulence is low, there is a small diffusion in momentum, small shift of the particle energy, and a greater probability for the particle to be diffused. So this was just to close what I have started yesterday for our piece of discussion of the transport equation. So what I would like to study today with you is to discuss a little bit in more detail all the pieces of the transport equation of a particle in the galaxy, or, I mean, I will do that mostly in the galaxy, but I would like that it get clear to you that this is true for any environments in which you want to propagate your particles. If you deal with extragalactic configurations, you have to adapt the numbers and the astrophysical environments. The same applies, or vice versa, if you want to study the environment and the diffusion around an astrophysical source, around the pulsar, around the supernova remnant. The equations are these ones. And the physics, so the transport, the nuclear physics that we will see in a while, and the elementary particle physics, I will remind you some Croc session today, just enters depending, again, on the astrophysical environment. So let me remind you the transport equation, and we will elaborate all the pieces. For a source that can be varying on time, we have the n over the t, and then we have the diffusion. So I told you I use both k or d, so you get used also to the literature notation, which uses both, plus this term here, and this is n. I write only once that it is dependent on energy, space, and time. And then we have the energy component, just what I was deriving with you today and yesterday. A coefficient, I will deal with it in a while, that I call B, minus C dn over dE. And then we have a term which is due to inelastic interaction, a term which is due to radioactive decay. This is N. And then today I will be a little bit more explicit in writing the sources, since yesterday I detailed a little bit. We have primary cosmic rays, and the source is Q, and very generically can be a function of all the variables. And we can have a secondary term, which is the production of spallation reactions, and it is given by a term that I will discuss afterward, that includes all the nuclei which have a mass number AE greater than the nucleus we are dealing with. So the N that I'm writing here is for a specific nucleus or a species. I don't want to have a very heavy notation, but we are discussing one species, and one nucleus, or also some leptons, can be produced by spallation reactions. This takes into account nuclear physics of all the nuclei that are heavier than this one. I will deal with any term in detail. So, this is diffusion in space. This is a term that is called convection. This term B is due to energy losses. This term, whose coefficient is C, is right what you have derived now. And this is linked to energy gains. It is the reacceleration substantially. This is the destruction due to nuclear processes. And these are the sources. Good. So let's study this equation in more details. I will tell you very few words about the convection in the galaxy. The convection in the galaxy is a phenomenon which we believe is occurring in the Milky Way because we observe external galaxies. The presence of a convective term is due to the effect of a wind, practically due to the stellar activity, and this wind very likely flows, if this is the disk of the galaxy, the wind flows outside the disk and grossly in a vertical direction. This is the galactic wind, and the speed of the galactic wind is some convective velocity. In principle, it is a vector, and in principle, it is varying with the height from the galactic plane. The fact that this convective wind is present is, well, of course, due to the astrophysics that we know from for our galaxy, but also to the fact that we have observed external galaxies having radio emission at some eighth above the galactic plane. That means that these particles are flowing outside the disk in a diffusive halo where this wind is active. So I don't want to spend too many words. I think that this physics is, somehow easy for you if you encounter it at some point. The form is not clear. Of course, the problem of being inside our galaxy is somehow reducing our observation opportunities. We are a bit blind when we are inside. Anyway, these terms usually has to be taken into account with a counterpart, with an associated term, which includes adiabatic losses due to convection. But this is the only point that I want to detail to hint for convection. What is a bit, in my opinion, more centered on the topics of this school is a discussion on the energy losses. Energy losses are the first pieces when one deals in the physics of cosmic rays that needs another knowledge of physics, because to treat energy losses, we need QAD, QCD, and nuclear physics. So the first astroparticle action that we do when dealing with cosmic rays is writing these energy losses and trying to remember what are the Croc sessions that we need to include. And now I will deal with them both for nuclei and for leptons. Nuclei and leptons are experiencing different energy losses. So let me first list the energy losses that nuclei, isotopes, are experiencing in the galaxy. And these energy losses that enters in the term B, BDE, and sometimes are written also in this way, are of two types. For nuclei, maybe you can think about it. So nuclei are hadrons, and they travel in the galaxy, and they meet hadrons, so the interstellar medium, which is hydrogen and helium, and they meet electrons. So which are the two types of energy losses that they can encounter? One is ionization, if the medium is neutral, and the other one is Coulomb energy losses. So nuclei suffer ionization losses, and this happen on neutral interstellar medium, which is the most of the interstellar medium, indeed. And Coulomb energy losses in a fully, or anyway, in an ionized plasma. So, one Croc session that will appear very often here, you should know better than me, you are much more fresh of your studies, is the Thomson cross-section. Okay, so I just remind you the expression for the Thomson cross-section that it will enter in our formula. It is AP 8 pi divided by 3, the typical electron radius squared. And the electron radius is the square of the charge divided 4p divided by epsilon 0, electron mass c squared. You can also write in terms of constant, which is the fine structure constant, h, and the speed of light, mass of the electron, c squared. And if you put numbers, these are all constant in nature. And this sigma Thomson is 6.65 10 to the minus 29 square meter. Remember that a barn, which is the typical unit for cross-section, is 10 to the minus 24 centimeters squared. And that is 0.665 barn. So just to give you some numbers that are useful. So few words about ionization energy losses. The variation of the energy over time, this should have been something that you have computed. I don't know your specific background for your undergraduate studies, but I think that you should have computed at some point. Anyway, I remind here so you can recover your notes. For any speed greater than beta zero is the speed of the electron bound in the atom. And beta, of course, is the particle speed that we are dealing with. And this expression is equal to minus 2p, the electron squared, which is written here, the typical radius of the electron. Mass of electron c, this is c cube, divided by beta. And then there is a sum on n times bs. So S is hydrogen and helium in the interstellar medium, and NS is the density of these particles. So you see that, well, nice, this is a cross-section, but it involves the density of the particles. So you cannot avoid this computation if you don't know the distribution of your targets in the galaxy. And this term, Bs, is instead a pure particle physics term. I just remind you that it goes as a logarithm of 2mc squared, beta squared, gamma squared, some maximum quantity Q, divided by the ionization potential of the scatter centers, minus 2 beta squared. So B0 I defined is the velocity of the electron. IS are the ionization potentials for the nuclei in the interstellar medium. They are of the order of few tens of electron volts, to give you also a feeling of the quantities. Then we have this Qmax, which is twice the mass of the electron, C squared, beta squared, gamma squared, and then we have 1 plus 2 gamma, and then we have the ratio of the masses. This capital M is the mass of the nuclei of helium or hydrogen. The density, the mass of the targets in the interstellar medium. So this is the expression that at some point you must deal with in order to put the first pieces in this term B as a function of E. Good. Then we have energy losses. Due to Coulomb scattering. And in this case, I think you did at some point also in your previous studies anyway, I remind you what it is, the Coulomb scattering formula. So you have the surface of the electron sphere, and then we have C times the mass of the electron, C squared, Z squared, NE logarithm of lambda, and then we have beta squared, X M cubed plus beta cube. So, many constants are clear to you. This scattering, of course, is enhanced for high Z targets. And the density of the electrons that we have to put inside, again, is a parameter that we must know, we must derive from astronomy. So in order to compute this particle physics effect, we have to know how many electrons and how they are distributed in the galaxy. And this is a multi-wavelength and multi-messenger, as before. Ingredients, we are not able just to put a number without making observations of the plasma and models and using many data to derive. This huge activity brings us to an estimation of this electron plasma, which is 0.03 ionized, so electrons per centimeter cube. This is an average in the galaxy. Then we have other terms. We have this logarithm of lambda, which is more or less 1/2 the logarithm of, let me just briefly write a function of the electron mass, the target mass, and fundamental constants. So I don't want to spend too much time on this. But instead, this quantity that it is written here, which is xm, is given by a coefficient, a number, which is 3 times square root of pi divided by 4 taken, this is this 1/3, so a number. But then we have the square root of twice k, the Boltzmann constant, the temperature of these electrons. So not only the density is necessary, but you should also know the temperature of this plasma. And again, you start, if you have to do this work, you start reading astrophysics papers to understand which is the typical distribution of the temperature you see here. This reminds you thermodynamical equilibrium, of course. So even in the simplest cases, the two particle physics and the astrophysics of the gas in the galaxy are strongly connected. These energy losses, I told you, are for nuclei, while electrons suffer different and much more dramatic energy losses. So now we concentrate a while on the energy losses for the leptonic part of the cosmic radiation. So in the following, I will often say simply electrons, but of course, anything is true for both E plus and E minus. They just have a charge difference. These particles, differently from nuclei, are dominated by energy losses. So E plus, E minus suffer very violent radiative cooling. So they lose energy because they radiate enormously. And the two most important phenomena that affect the propagation of electrons in the galaxy are synchrotron emission. So let me just make a step back. Now I'm discussing energy losses. But anytime this particle lose energy, they also emit a radiation. So the fact that I seem to confuse losses and emission indeed is because it is the same physics that from one side you consider as a loss of energy for the particle, but on the other side, if you can observe this radiation, it is an emission of the processes that is occurring to leptons. So we have synchrotron emission or loss, and the other one is inverse Compton. I will call it briefly IC scattering. For these particles, the Bremsstrahlung, the Compton and the Coulomb and ionization energy losses are negligible. These energy losses are pretty well described in a paper which is dated back to many years ago, Blumenthal and Gould. QED was already pretty well established, so in 1960. And then there is a book by Rybicki and Lightman, which is radiative processes in astrophysics. So you can find the details of this. So let me remind you or tell you what is the synchrotron loss or emission. We have a magnetic field. B, and any time a particle, for example, an electron, travels around this magnetic field, it emits, it loses its energy and emits photons. So the synchrotron emission or losses is the interaction of E plus E minus with magnetic fields. I give you the expression for this typical energy loss. Which is the following. So the variation of energy with respect to time and frequency so if it is a loss, there is a minus sign. If you compute very often, you see this expression not with the minus, but with the plus, because people compute or are interested in the emitted radiation. Okay, so it depends if you consider a loss and you put it in the diffusion equation, or if you want to look at the waves, the electromagnetic waves. So, for example, in all this literature, you find a plus. This is just to... And this is the square root of 3, the charge cube, the magnetic field, divided the mass of the electrons, by times a function. So what I want to underline here is the dependence of this loss or emission on the magnetic fields. So in the first two pieces, we had to know the distribution of plasma and gas and its density and its temperature in the galaxy. In order to compute this, we must know the magnetic fields of the places in which these electrons are traveling and are losing their energies, which again is not that trivial. This function is dependent on x, and x is the frequency divided by a critical frequency. So the frequency is the frequencies of the emitted photons. And this critical frequency is given by factors b e squared, again factors here. If you take typical magnetic fields, what are typical magnetic fields? Well, of course, it depends, but the magnetic fields that are filling the disk of the galaxy are of the order of the micro-Gauss. So 10 to the minus 6 Gauss. From this formula for the typical, this critical, this it is indeed the frequency at which you find most of the photons. You can compute the value of the frequency. You can do yourself by an exercise. So you put here micro-Gauss or few micro-Gauss. All the rest is given by tables, and you decide an energy for your electrons. And that gives us the result that for, let's say, electrons at energies greater than the GV, for magnetic fields of the order of the micro-Gauss, the synchrotron radiation occurs at radio frequencies. We will derive it in a while. Okay, yes, I had, in fact, my notes on that. So Gx is a function that one derives when doing this the computation for the elementary process. Anyway, I just write you the expression. It is the integral on the direction, the relative direction theta. There is a function which is a function of x, and this sinus theta, and it is the omega over 4 pi. And this f function is connected to some modified Bessel function. So it's, don't want to give you too many details of this. You can easily find in the books. But this is the result for, I mean, this function depends on x, so it's a function of frequency. Of frequency, you see here, x is the frequency divided by the magnetic field. So it is connected, and to the energy of the charged particle which spiralizes around the magnetic field. One can derive the frequency, which I call nu max, which is a bit different indeed by the nu c, and it is the frequency at which we have the maximum of the emission or the loss. So the maximum of the emitted power by the synchrotron interaction is nu max, which is the frequency at which we have the maximum of the emitted power, or if you want, the maximum of the energy loss. And it is more or less approximately given by 2 gamma squared times the magnetic field measured in microgauss. So now you can just take maybe a few minutes of your time to compute yourself at which frequency you expect. I already gave you some hints. So imagine to have electrons at 100 MeV. You know the gamma, it is the Lorentz vector. And typical magnetic fields in the galaxy, I told you, are between 2 and 6 microgauss. You can do the exercise for E equal to 0.1 GeV, or for example, for 10 GeV, or any. So you can just try to compute yourself 2 minutes, and I will give you the results in a while. You compute nu max, so the frequency at which you expect the most of the loss or the emission for synchrotron radiation of leptons in the galaxy. Imagine to be interested to study this emission, you should at least understand which kind of telescope you need. If it is an X-ray or a radio or whatever. So the number that you find is in units of second minus 1. So this approximated formula is for Hertz. So people who computed for 100 MeV, which number have you got? No number, sorry, it was an exam, I didn't tell you. Dario, we have to start again. No certificate. And then it depends if the answer is wrong or right. We write. 10 to the 5 hertz. Yeah, for the, yes, more or less, yes. So let's, and for 100? No, it was not 100, it was 10. It is of the order of gigahertz, yes, for 10. So Numax for 100 MeV electrons is equal to 2, gamma, which is 100 MeV divided 0.5 MeV, more or less. This is squared. We can put 4 for the magnetic field in terms of, in units of microgauss. And so this is 2, if I'm correct, 4, 10 to the 4, times 4 hertz, which is, yeah, some 443, 10 to the 5. And if you put, if you compute for 10, for electrons or positrons of 10 GeV, you are at the gigahertz. Which is, of course, yes, it is a big energy. So depending on the energy of electrons, we have a synchrotron radiation, which is mostly in the radio band, and which can be measured by radio antennas, by radio telescopes. So if you know that there is a source which is losing energy by synchrotron, you should make an estimation of the energy of the electrons, and then you can estimate which is the most convenient frequencies at which tune or build your telescope. Okay, for synchrotron it is almost done, unless I want to make a connection with the typical time at which these effects occur. One can write an approximated formula for the synchrotron emission, which is proportional to sigma t, the magnetic field, and gamma square. But what it is important is that from this expression one can compute a typical time at which electrons lose a significant part of their energy. And the typical synchrotron time, you can do a derivation and put the constant terms, so it's too long to derive in these lectures, but I think that in principle, you have all the tools surely to understand, but also for do the computation yourself, is a coefficient which is a 300 E divided 1 GV minus 1 B divided 3 microgauss to minus 1, and this is, well, I have to check this number. I will tell you later. I'm not sure about this, but yeah, probably it makes sense. And if you have, for example, let's make another example, electrons at 1 TeV. Yes, the typical synchrotron time is 0.3 megayears. Yeah, it makes sense. Now, let's come to the other process that strongly affects leptons. I will give you again some hints. Everybody of you, I hope you all have done classes of QED in your undergraduate studies. So at some point you have computed or you are able to compute a Compton Croc session. So of course we don't compute the Croc session here, but I remind the main pieces. Inverse Compton is nothing else than a Compton scattering, where inverse is some fancy name just to say that the kinematics are opposite. We see now the Compton, inverse Compton energy losses, which are, of course, also an emission. And the process is the following. Imagine to have a population of photons and very energetic electrons scattering on these photons. The inverse Compton scattering implies that after the interaction, you have the electron, which has lost part of its energy, and the photon is up scattered in energy. So the target photon has an energy E, and the final state photon has an energy E prime greater than E. So it is a process by which very energetic leptons transfer, upscatter population of photons. So it is inverse just because of the energy transfer. So the point is that we have relativistic electrons. So these are our electrons accelerated by first-order Fermi shocks, for example, that travel in the galaxy and encounter populations of photons. This bath of photons, that is the target for these electrons, is called interstellar radiation field. So you start to understand that, well, in addition to QED, one should know all this population of photons, which is, again, a work that astrophysicists should do. The QED computation can be done in two kinematic regimes. One is the Thomson regime, and the other one, for very energetic projectiles, it is the Klein-Nishina that you probably have done in the past. So the Thomson regime is valid whenever the Lorentz vector for the electron is smaller, more or less, than the mass of the electron divided by the energy of the gamma rays. And again, we should know what these gamma rays are, and I'll come in a while. So, which are the photons, in your opinion, that fill the galaxy? I mean, which kind of frequencies or energies we should deal with here? Well, yes, I heard somebody. Unavoidable, whenever you turn around, you cannot avoid, is the CMB. So you have studied also last week. It's everywhere, and I would say forever, just a bit redshifted, but you will find them. So, photon population, because we cannot write any compute. We can write the Croc section, but we cannot compute if we don't know the photon bath. So, I'm discussing the interstellar radiation fields. One good is CMB. Typical energy for the CMB, I don't know if you have computed, maybe not last week. Do you have an idea which is the energy, typical energy of photons in the CMB at 3 keV? It is small. It is about 2.4 10 to the minus 4 eV. Okay? Then, we have the infrared light that fills the galaxy because of stellar activity and dust and so on and so forth. And the typical energy for this population of photons is a bit higher. It is 3 point something, and it is 10 to the minus 3 electron volts. And then we have surely another relevant population of photons, which is the optical. You see stars in the sky, and they emit, and the average energy is some 0.3 electron volt. This is the average emission. Remember the quantum mechanics derivation of the hydrogen atom. There is 13.6 electron volt. This is for the ionization of the hydrogen, but the energies for optical processes are, let's say, electron volt or a bit less. Nice. But not only we have to know the energy, it would be useful to know also the distribution in the galaxy, which is far from trivial. So before, again, starting the computation of your QED Croc session, you should stop and write down, derive, ask to your astrophysics and astronomer colleagues, which are the distribution of the, well, CMB is easy, but I mean, since few decades, it is easy, at least since COBE data, it's done. But the other two are really very difficult. So, in the hypothesis that we have this distribution, maybe I can show it before going on. So, this is a piece of work that we have done a few years ago, and it was not, ours was not the most heavy work, because all these points that you see here are derivation, very complicated derivation for the averaged interstellar radiation field at any of these energies. So we just fitted these data points with black body distribution. So that the CMB is a black body, again, is safe. For the other populations, it seems that it is safe as well. This is the three population. You see here we start to be close to the energies in the optical. So these were just very few indicative numbers. The life is much more complicated than that. But in order to compute the Compton scattering, you have to analyze the emission at a huge number of wavelengths in any place of the galaxy to make an average or to write a map according to what you need and what you can do. And then if you want to make some computer prediction, you can try to fit this population with a black body so that you don't lose hours or days of computation just for energy losses. Okay, so this is even one slice, because we have made some average, different average in the galaxies you can do, and you see that results are not the same. So this is the target of inverse Compton. And to come back to our numbers, we have that the Thomson regime that I wrote just at the top of that blackboard. Is valid for electrons that are lower in energy than very high energy, let's say. This is the PV, okay? Only if the scattering, the inverse Compton scattering, is on CMB. So what I'm saying is that if you have electrons with energies smaller than the PV, and you are treating a place of the universe in which you only have CMB, you can safely use the Thomson approximation. If the interaction is on the infrared population, then this number is 8 to the 4 GeV. So if you increase the energy scattering, the energy of the scatterers, you decrease the energy below which Thomson is valid. So you start needing maybe treating Klein-Shina. This is particularly relevant when considering the stellar light, so let's say the optical wavelength, in which, for which all the photons, all the electrons with energy smaller than few TeV can be treated with Thomson approximation. Otherwise, you have to take the more complicated Klein-Shina. So now I don't write all the stuff for for the Klein-Shih approximation. I think it's getting to take too much time to me. Again, I just want to write very quickly. This is the number of collisions, so finally you can go back to the Croc session. It is a function of, in principle, of time, of photon energy. I have written E gamma plus. And this Croc session has a huge QED part, but involves the distribution of photons, which is just the figure that I put them. Okay? And then you have energy masses, h, c squared, c cubed, and so on and so forth. So this quantity, well, we have written omega, but anyway, is the photon density. So it is unavoidable to make cosmic ray physics without having data from many, many wavelengths. In the Thomson regime, only if you deal with Thomson regime, the energy loss by inverse Compton is proportional again to this Croc session, the population of your radiation, so this is linked to this dn over the E gamma, and gamma squared. So now, before proceeding with other pieces of information, I want to show you what happens to electrons traveling in the galaxy and suffering with these energy losses. So this is, thank you, Dario, one first slide. The energy loss can also be, let's say, somehow connected to a typical time, which is what I just computed in the first case before. This is the typical time, which is 10 to the 16 seconds. You can transform into mega years. An year is 310 to the 7 seconds. So this is the term BE, which enters in the diffusion equation, just normalized to E squared, because many of these processes go grossly as E squared. Synchrotron emission, if the magnetic field is constant, is a constant term. And it is this one. And inverse Compton is this one. So you can see that there is an energy which is above 10 TeV, in which the two have opposite change their mutual relevance. And this is the total. This is just for indicating that often in some simple computation that people do, that one can do, the energy losses are put in constant to this number. So it is an approximation which is indeed no more valid for very high particles, very high energy particles. This is for after. And this is a figure that it is specific for electrons. So let me try to explain you what we have done here. This is a fraction. And this is the fraction of electrons, or E plus E minus, that arrive at the Earth from a distance which is marked here from the Earth. So here it is the Earth. We have sources around us. Electrons are emitted from these sources and lose energy. So very, very far electrons cannot arrive with this very high energy to the Earth. So take, I don't know, 1 kiloparsec, which is here. And look the solid lines. For example, this is for 1 TeV. So 1 TeV electrons arrive for, I would say, 90% grossly, a bit less, 80%, from sources located at 1 kiloparsec around us. And the point that they don't arrive from farther sources is due to energy losses. So if we want, this is, in my opinion, an important message. So if we want to study our, not universe, let's say galaxies, by means of electrons, we must be aware that we cannot test very large distances, very large portion of the galaxies, because these guys lose energies, and they don't arrive, or they arrive with a very much decreased energy. Take, for example, this is 1 GeV electron. Well, this is a bit, I mean, they can come from farther regions. So 90% of 1 GeV electrons, well, I don't see very well now here, but come from 3 kiloparsecs sources located at 3 kiloparsecs from us. So this is kind of electron horizon. And these electron horizons is due to QED processes convolved with distribution of photons and magnetic fields, because it is here inverse Compton and synchrotron radiation. Now, let me just say a few words about the the dotted or dashed lines. The full model means that we have included the relativistic correction of QED cross-section due to Klein-Shina. The simplest way is to use Thomson for everybody. So including Klein-Shina makes this difference from here, if you only use Thomson, to here. What does it mean? The Klein-Shina cross-section decreases with respect to the Thomson. If the cross-section decreases, this is, well, not really physics at the blackboard, it is physics with arms, but too much blackboard. So if the cross decreases, no, I should orientate, otherwise it is terrible. So I orientate towards you. So this is high, and this is small energies, and this is high energies. If the cross-section, Thomson is this way, and Klein-Shina is this way, it means that energy losses, in the full relativistic case, are less effective. If they are less effective, the flux of electrons is higher because they don't lose so much energy, okay? And it is visible here, because if you take 1 TeV in Thomson, or with the full the full relativistic, it means the full relativistic, in order to have 80%, you have to go here. Otherwise, with Thomson, they are much closer because they arrive and they don't lose energy. That should be the explanation. Yeah. Okay. Now, I still have some time, and I go back to an effect that involves nuclei, but which is not given by QED or Coulomb or whatever, but it is real nuclear physics. And then I will show you a total, a picture with processes also for nuclei. So up to now, we have studied this term for nuclei and for leptons. Now we go to this piece here in the diffusion equation. That means that you have some nuclei. So you have a nucleus, I called it J, for example. This little guy can interact in a catastrophic way with the interstellar medium nuclei, which are, again, always made by hydrogen and helium. These are kind of relic of the Big Bang, the proportion. And it destroys itself. So we lose this nucleus because it goes to another whatever, plus, which I just put X to say any hadronic final state. So N disappears. And not only it can decrease its energy, so the fact that this effect is not in the energy losses term is because it not only loses energy, it destroys. So we have to subtract all the particles that in their wandering in the galaxy lose themselves, because of destruction. And the destruction term, which is in the diffusion equation, which I call gamma for inelastic scattering, again, is a mixture of information on the interstellar medium. This is the density of the interstellar medium. And again, you have to have a map of hydrogen and helium, or at least an average value. The speed of the particle, well, since you compute it, it is easy. It's an input of your code. And then there is another box, which is the Croc session. At some point, we are faced with this quantity. And this inelastic Croc session, you have only one way to know, to measure it at colliders, or having very complicated nuclear models. But so far, in the propagation codes that people is using for computing cosmic rays in the galaxy, practically the only way is to have data, and these are not so frequent, and to try some very empirical fitting and modeling of the data. But not only we need all the astronomy and astrophysics for magnetic fields or interstellar radiation field, but also should discuss and should see with our high energy physics colleagues how to have this data. So the relevance of the destruction in the diffusion equation, in the transport equation, depends on nuclear physics, and it depends nuclei by nuclei. Of course, the greater is the Croc session, the smaller is the typical time that a particle travels before disappearing. So again, the typical time for inelastic scattering, one can derive, and it is 1,000, the density of the interstellar medium normalized to 1 particle per centimeter cube, -1, and sigma inelastic normalized to 1 millibarn, -1, and units here are megayear. So if the Croc session is 1 millibarn, the typical time is, let's say, hundreds of megayear. If it is barn, this number is decreased by a factor of 1,000, and the particles very rapidly, of course, according to the typical galactic scales, disappears. For Croc session, now I don't want to open this chapter here, which maybe I will touch the last day, but only give you some very rough diagram. So this is the energy. This is the inelastic Croc session, which is measured in millibarn, and typical values are hundreds of millibarns, depending on the nuclei, of course. I'm just doing some very generic estimates. For example, the Croc session goes more or less this way, or this way. In the first case, it is proton over beryllium, and this is helium over beryllium. It is, I mean, just one Croc session. It's not even relevant. There's scatter here, not that much. The point is the following that I would like to make clear to you. So imagine that we want to use this transport equation and compute whatever nucleus or isotope that you are interested in. Proton is easy, but maybe you want to know the carbon-12 or whatever. You must be aware that there is a cascade of nuclei that must be included in a full computation. Usually, the full propagation codes that try to solve this equation start from iron or even from nickel, which are the highest nuclei produced in thermonuclear fusion of stars, so they can be the seeds of particles accelerated by supernova shocks. And one has to compute from the heaviest to the lowest, take into account all the isotopes and all the reactions. So for every isotope, kinking, spallating over hydrogen and over helium, in principle, you must know a Croc session. So the work of including Croc session in the codes is enormous. And is enormous for two reasons. One, because you have hundreds of processes. Some processes are negligible, others are relevant. If you want to be precise, you include all. And the other one, because you ask a PhD student to spend significant part of the time looking for data, because it is a very heavy work for that. Of course, some colleagues have done this part, our group, other groups have done, but it is a very, very relevant and difficult part of propagation codes. So maybe I just show you this last figure. Now, grazie Dario, it refers to nuclei. I'll show you before 2 figures for leptons. And I'm arriving only now to nuclei because I wanted to add this non-electromagnetic part for them. And in order to be acquainted with the different quantities, here there is plotted the time in mega years. So I hope it is clear that the shorter is the time associated to a process, the more effective is this process, because it happens quickly. So this line we have written here, escape, it means diffusion. Diffusion means this term here in the diffusion equation. And everything is done for protons, unless this line, which is for iron. So take protons. Protons, for energies, let's say, above hundreds of MeV, so low energy protons, let me say, for cosmic particles, are dominated by diffusion. That makes sense, because protons do not break themselves so much. The destruction of protons is very small. And, well, this wind means convection, which I just hinted to you. And spallation of protons has very huge typical times. That means it is negligible with respect to diffusion in space. That is not true for iron. Iron is delicate, maybe it's too much, but it is a nucleus that can break easily, much more easily than other nuclei. So spallations for iron are very important, and at least for 10, this is GeV per nucleon, so the kinetic energy of iron here is 10 times 56 GeV. So spallations for irons cannot be neglected at energies at which we have data. I will show you that we have data in this region here. They can be neglected for protons. So nuclear physics can strongly affect our computations for nuclei. That's all for today. Thank you.